Good morning, everyone. Thank you, Dario, for the very nice introduction, and thank you to the organizers to invite me to the Swiss Robotics Day. So I'm going to talk on from drone racing to space, pushing the limits on vision-based AI. And Dario mentioned a competition that we organized a few years ago, and let me start directly with that. There should be sound.
It's beautiful. One day, I dream I can achieve that. Damn.
You know, that's not human.
Man.
Insanity.
I don't even know what I just
so
watched.
happy to see that in person. That is beautiful. One day, I dream I can achieve that. Damn.
I always get shivers when I watch this video because it was a lot of work, 7 years of work, a lot of students involved. And so what you witnessed there was the first AI versus human drone race, during which our AI-powered drone outperformed the 2 world champion drone racing pilots. And I want to tell you today the story that led to that, why did we do it, and so on. The results were published in Nature, and we were very happy that Nature dedicated the cover to this result because it was a historical result. It was the first time that an AI defeated a human in a physical sport. A lot of students, master students, PhD students, visiting researchers were involved, so it was a big team effort, and I'm truly proud of the team. But now, maybe you're wondering, why did you do it? And was it worth it? What did you learn? And what's next? So I'm trying to go to answer these questions today. But I have to make a step back to 10 years ago to the first vacuum cleaning robots that were commercialized by a company. And what you see here is a long exposure picture of a Roomba autonomous vacuum cleaning robot. And what you can see is in order to clean a room of about 20 square meters, the robot would take until that time around 20 minutes. Not truly competitive against humans, right? What happened in 2015, so 1 year later? The company installed a camera and a computer. They ran SLAM, simultaneous localization and mapping on board. So the robot was, for the first time, capable of following smarter trajectory. So what's the bottom line of the story? Thanks to perception, the robot became more agile and therefore more productive. It was able to increase the productivity from 20 minutes to just 5 minutes. Is it more productive than humans? No. It takes me around 1 minute to do vacuum that size of a bedroom. But where else has perception played a crucial role? For example, in legged robotics. This is a very famous video of Boston Dynamics Atlas doing parkour. And these feats were actually made possible by perception and model predictive control. So the robot used as much as 4 cameras that were 3D mapping the environment, predicting the next footsteps, and then the controller was taking care of accommodating the next plan with the uncertainty in the perception. Where else has perception played another pivotal role? Well, for example, in space. What you see here is the first flight of Ingenuity, the first drone on Mars by NASA Jet Propulsion Laboratory, which used a single onboard camera and a computer to fly autonomously on another planet. So when you look at these videos, what you can see is that perception, that we call computer vision, is making mobile robots autonomous. But when you look around, where are the robots? Humans are still preferred in most applications. Why is that? Because current robots are far from human performance in agility, versatility, and robustness. So in my lab, we are trying to tackle these 3 challenges. But rather than working on any robotic platforms, we focused on the drone because the drone is one of the few platforms that without seeing, it cannot even fly. And we set for ourselves a very ambitious goal. What does it take to fly autonomously a drone better than a human pilot? So what you see in this video is an expert human pilot piloting a drone through a racing course. Now, expert human pilots take several years to achieve the skills that you see in this video. When we started this research, we thought that the reason why humans are so good is because they are faster than machines, and we were wrong. So in this paper, we measured the reaction time of expert human pilots at drone racing tasks, and we measured it at 1/4 of a second, 250 milliseconds, which is a lot, because our algorithms are 10 times as fast, 20 milliseconds. So the conclusion of the study was that human pilots are not better than machines because they are faster, but because they can make better decisions in complex situations. And that's the reason why we don't have autonomous cars, because a human driver makes an accident every 100 million kilometers. Now, you may be wondering, why do you care about making drones more agile, especially with all the things that they can be misused for? Well, because of the same reason I told you before, from Roomba vacuum cleaners to Boston Dynamics Atlas to parkour and other things. Agility means productivity. We want robots to help us, so they should be more productive than us. But particularly for drones, a drone that flies faster can fly longer distances, so it can fly farther. And this is very important for search and rescue, inspection, wildfire prevention, and space. For example, the next Mars helicopter, which is planned for 2032, is expected to fly 10 kilometers instead of 300 meters like Ingenuity. So we'll need to actually fly much faster than Ingenuity. But now the problem is when you try to fly autonomously fast, there are challenges. There is no free lunch. So you have motion blur, you have overexposure of the camera because the camera direction is changing very quickly, and you have a lot of aerodynamic effects. So what we have done over the past few years is trying to combine standard classic first principle models based on optimal control and computer vision geometry with deep networks in order to increase the generalizability and the agility of our flying machines. Actually, thanks to the introduction of machine learning models, we were able to fly for the first time out of the lab and achieve the feats that you see in these videos. Like, for example, doing acrobatics with a performance similar or undistinguishable from human pilots. What else were we able to perform? For example, here you see the same drones doing slalom in a forest or up to 40 kilometers per hour, or in a search and rescue environment, and even exiting a hangar through a narrow door, outperforming commercial platforms like this one. So this was achieved thanks to deep networks. But as you know, deep networks require a lot of data, and you cannot rely on data collected in the real world. So what we did is that we resorted to simulation, because simulation is fast, is cheap, and is most importantly safe. And it allows you the collection of unlimited amount of data. What we did is that we were able to train these algorithms, these models in simulation, and transfer them to the real world, zero shot most of the time, so it means with any fine-tuning in the real world, or sometimes with a little bit of fine-tuning in the physical world. What you're going to see here is a time-lapse of the algorithm behind the drone racing AI drone that defeated the world champion. So here we built a digital model of the environment and of the drone, and the drone learned to first fly and then race superhuman thanks to an algorithm called reinforcement learning that is trained via trial and error. Here the drone was undergoing more than 20 million time steps, so a lot of episodes of trial and errors, making a lot of mistakes to first learn to hover, then to fly, and then become superhuman. But how far were we from human pilots up to that point? So after 7 years of work, that here I condensed in just 5 minutes, we thought that we were ready to compete against the world champions. So we started a dialogue with Alex Vanover and Thomas Bitmatta, the 2 world champions of the 2 main world drone racing leagues, and we invited them to Zurich. And they were very young, less than 20. They came with their family, parents, and so on. Most of the champions are very young, because that's when your reflexes are fastest. And most important is to say that both the human drones and the AI drones were identical. So same camera, same mass, same aerodynamics, same field of view, same frame rate. Everything was identical. It was a fair AI versus human race. And let me show you the footage of the final performance. The AI won, otherwise I wouldn't be able to tell you today the story. And it won with a lead time of 0.5 seconds, which is significant because in these competitions, the difference between first and second place winner is usually 0.1 seconds. In addition, the AI won the majority of races, so 60% of the races, which was 15 out of 25. But when I show these videos to people, people think, okay, is therefore the game over? Does it mean that now AI is better than humans? And if you are working or researching or studying robotics, you know very well that the answer is absolutely not, because robustness was not taken into account. And that's actually the next challenge, not just for my lab, for every other labs, and also for all the companies. You know, when you take these competitions done autonomously in the other environments for which they were not trained, well, differently from human pilots, they start crashing a lot, but it's not just for academic labs, it's also for companies. So robustness is truly, truly difficult. That's why we don't still have autonomous robots around us. But talking about robustness, then the big question is, then what's next? Well, let's look at nature. Let's look, for example, at sparrowhawks, because now when you look at drones, the only most agile platform after a superhuman drone racing champion is actually the sparrowhawk. They are truly capable of flying through narrow gaps and slalom at impressive speeds. The reason why they are so agile, it's actually not just the mechanics. So let's assume that the mechanic was the same as a drone. If you look only at the perception, the reason why a bird is much more agile than any machine is because their vision system sits on the aircraft. Think about it. So it doesn't consume images coming at 30 hertz through a standard camera, frame-based, but it consumes pixels, photons actually, coming continuously in time. We don't have frames, we have photons that are continuously integrated and sent to the brain. So can we replicate this in technology? Yes. Professor Toby Delbruck at the Institute of Neuroinformatics of the University of Zurich 15 years ago invented and commercialized the first event-based camera, also called the neuromorphic camera, because it mimics the working principle of the human eye. It has independent pixels that only trigger information when there is change, which is caused by motion. So if you move your arm, the camera will only react to those parts of the scene that are moving. What are the key advantages? It has an incredibly low latency in the order of microseconds and very, very low bandwidth. So you don't need a GPU in order to process these things. So you can do impressive things, like, for example, dodging objects thrown at the drone while the drone is in forward flight, things that would be impossible at these relative speeds with a standard camera, unless you use a GPU, because all you need is low latency. So the only way with a standard camera to have low latency is to basically process a lot of frames in a limited amount of time, which will require a GPU. Other things that we were very recently able to do was, for the first time, to fly a drone in a very narrow pipe. And we are going to give a demonstration live to you at booth number 25 today. This is actually the first time we are showcasing this to the public. It's a paper about to appear. So what are the problems when you try to navigate a drone in a pipe? There is a lot of turbulent flow, which is impossible to model. The only way to do it would be to use very high-speed cameras, but they are super expensive. They cost more than 100,000 euros. We were able to do this using the event camera for much, much cheaper, for a few $100. And the drone was able to actually fly by estimating fluid dynamics, velocimetry in real time, and using this as a feedback loop for autonomous control. Where else have event cameras already played a role? For example, in automotive, you can see that the output of an event camera is complementary to that of a standard camera. And in automotive, well, this is a sector where safety is of utmost importance because you want to save people's lives. And thanks to an event camera, what you can do is that you can enable inter-frame object detection. So you can detect pedestrians, other traffic participants, even before they are detected by a standard camera. So we showed in particular that if you combine an event camera with a standard camera, you can achieve the same latency as a 5,000 FPS camera, but with a bandwidth of a 50 Hertz camera. And there is a lot that this would unlock, like a Pandora box. And let me take you to one inspiring thing. So for the last half a year, I was working as a visiting researcher at NASA Jet Propulsion Laboratory for the next Mars Science helicopter planned for 2030. And space is actually a venue where all the things that we study robotics are very, very important. State estimation, aerodynamics, control, everything. Low latency perception, low latency bandwidth. And let me show you one of the things of the project I was involved in where all these things actually come into play. And there is sound. This is a concept by JPL. And I would like to thank you for your attention, but it's not over. We are going to give you also a live demo in a minute.
Thank you very much, Davide. So we received a few questions here from Slido. Just maybe I can group 2 or 3 together. The first question and the other one is, how do you handle multiple tracks? If you have a small variation in the track, and the second is, how can you generalize or scale these technologies to unstructured environments, and what type of real-world applications do you see?
Very good, very difficult question. So generalizability in drone racing can be achieved, for example, through domain randomization, where basically what we do in simulation is that we expose the policy, so the AI algorithm, to all the features that you want your AI to be invariant to, from lighting, aerodynamics, and especially changes in the position of the gates. We are also working on algorithms that can actually generalize to different tracks. This is already possible. We are able to do it. But then when you now provide generalizability, you lose in performance. So then the policy is no longer going to be the superhuman one. So it's the same for human pilots. Regarding generalizability to unstructured environment and how can we use this in the physical world, well, the whole goal of this gamified research was not to just work on the racing, was to basically push the limits of vision-based navigation. Because what we tackled were a lot of problems. We had to make our state estimation, so localization and mapping, super robust. And when you fly at these speeds, actually motion blur is one of the detrimental problems. And so we came up with algorithms now that can actually really counteract motion blur, overexposure of the camera, that can work in any environments, for search and rescue, to inspection, and other things. And we also came up with solutions to very difficult turbulent flow and aerodynamic effects for which before we didn't have any solutions, and now are providing very useful for applications like in space or in high regimes, like also for airplanes.
Yeah. I think you have some surprise over there.
Yes. So we are going to give you a light demo, a miniature drone race with 2 autonomous racing drones. Of course, it's not the one that you saw in the videos. That one was much larger. It was like 1,000 square meters. The drones were flying at 100 kilometers per hour. But to make it safe for you, we made it miniature. So the drones are vision-based. You're going to see what the drones see on the screen there, and enjoy. So lighting conditions are an unsolved problem. As you can see, I would like to invite my whole team on stage and take the final applause, because there was a lot of work that went into this that you don't see just behind the scenes. So as you can see, robotics takes still a lot of engineers. Thank you, everyone.
Thank you.